Really chilling here. Alright, last time we did proof by exhaustion, which is where we prove something by testing every situation. Now what happens if one of those situations actually proves that your statement is wrong? Then you've got another kind of proof there, and this proof is actually usually called a disproof. And that's what we're doing today. It's the disproof by counterexample. So let's get cracking with that. Okay then, in a way very similar to proof by exhaustion, you just break your statement down into different situations and test it and look for one which actually breaks that statement. So you might have something very simple like x is greater than 3 for all x members of the real numbers. Then you just think, well, x could be 2. That actually disproves your statement that x is always greater than 3. So if it's that simple, let's just quickly get it down in some sort of sentence to remember that and go straight in with a nice little example. Okay, let's do that thing. Alright then, so we've got this little sentence here. Find an example that breaks a statement. And now I've got this example question here for us. Disprove the square root of x squared is equivalent to x. Now that's saying that it's always equal to x. So this is like our mathematical statement here, and our question is to disprove it. Thankfully we know that that means always equal to, so what we're going to do, we're just going to put some situations in and see if they are right. Obvious place to start, let's just start with 1. So let's try x equals 1. This implies left hand side is going to be 1 squared, which is 1 square root of 1 is 1. Right hand side is 1. So that's right, that's not disproving it. Let's try 2. Obviously, I think we know what's going to happen. 2 squared is 4. Square root of 4 is 2. The right hand side is 2. So that's still right. You might be thinking though that the square root of 4 might be negative 4. However, we've not got a plus or minus sign here. So if it's not got a plus or minus sign, you might be thinking, well, it should be that. But it's not got that plus or minus sign, so we're only taking the positive. At which point you might think, alright then, well let's try a minus number. A minus number squared minus 2 squared is going to be 4. It's going to be positive. Square root of 4 is 2. If you're only looking at the positive square roots. So now on the left hand side we've got 2. Right hand side this time we've still got that original minus 2. Contradiction. That's our counterexample. So once you've got that, you've got your disproof, but you just need to put it in a little sentence. So, x. End of proof. Easy as peasy. I know I said that this is a disproof. It says so in the title. But what you might notice from here is that if you've got a statement like that, you can actually prove it. Now, that might seem a bit weird, so let's just go into the next example in black. Alright then, this is quite a wordy question. Sometimes you get maths questions and it's actually just an English test in some sense. You have to interpret this into some kind of mathematical question. So what you might want to do is write it as an equation just to help you visualize it. What it's saying is you've got 2 irrational numbers. So we're going to say, we're adding them together. Sum of 2 irrational numbers. We've got a plus b, that equals c, where a and b are members of. So they are the real numbers, but we can't express it as a rational. So we're doing the set difference, the quotients. So it's any real number which cannot be expressed as a quotient. So that's an irrational number. And C is a member of... My purple pen's still working? Yeah, it is. All right. Okay, so we're going to put in some numbers. We want 2 irrational numbers. Pi and root 2. Let's type pi and root 2. So root 2 plus pi equals Now, I don't need a calculator for that to know that that is going to be an irrational number. It just is. We could prove it, but that takes some heavy, heavy proof. So we're just going to put a little question mark and say irrational. Damn it, it definitely is. What if we had two root 2's together? Well, then you'd get 2 root 2, which is irrational as well. Okay, so that's irrational. This is wrong. But here's the key thing. Root 2 plus root 2, irrational. What if we just take them off of each other? There's nothing in the question that says they have to be different. That's why we did root 2 plus root 2. So let's just minus them off of each other. So we've got a positive 1 and a negative 1. That equals 0. Is 0 irrational? Well, 0 could be 0 over 1 or 0 over 2. It's definitely expressible as a fraction. Bam! That's the job, okay? Now these two are really they're quite similar. You throw in some numbers, test it. But sometimes you give an algebraic expression and you have to prove or disprove that. Now, as I've said previously, a lot of proof is to do with prime numbers. So let's have a nice prime number, type 1. Let me just write it down. Our question this time is an algebraic expression. It's saying n squared plus n plus 1 is a prime for all n, which are natural numbers. Is this true? Counterexample, we have to look for a situation which breaks this statement. So we need to find an n where we stick it in there and it is not a prime. So let's just try 1. N equals 1 implies 1 squared, 1. 1, add 1 equals 3. So that one is true. Let's try another one. N equals 2. This implies 2 squared is 4, plus 2 plus 1 is 7. That's showing that it's correct again. Now let's try n equals 3. This implies 3 squared is 9, plus 3 plus 1 equals 13. True. Might be useful to get a list of prime numbers at this point. N equals 4. This implies, I'm just going to change pen. 4 squared is 16, plus 4 plus 1 equals 21. I hope you realise that 21 is actually 3 times 7. So this is a contradiction. This is not a prime. So again, do your little sentence to summarise. Since n equals 4 gives 21, end of proof. That is it. So these are all the kind of examples that you get for disproof by counterexample. But this question could be extended a little bit. And these are usually the part B questions. I'm going to leave this for you. If this was part A and this was part B, what if n was a prime? So the n that you put in, instead of being a natural number, it itself was a prime. So you could do this one, you could do this one, you could do this one, but this one, 4, is not a prime. So you can't do that. You can do 5, you can't do 6, you can do 7, can't do 8, and so on. So again, you have to do the exact same thing, but the numbers you're putting in are reduced in size. You've got a smaller set of numbers, which means it might be harder to find it. On the topic of primes, there's a very famous mathematical problem which was solved by counterexample, or rather it was disproved by counterexample. So a famous mathematician called Fermat had this thing called Fermat's primes, or Fermat's numbers. These are numbers which have, just do it in red, they can be written in the form of 2 to the power of 2 to the power of n plus 1. So n is any positive integer, which is not 0, but it's 1, 2, 3, 4, and so on. Now, if you put any positive integer into here, Fermat said that should be a prime. Now, you can do that and you can try it, and you can actually find a number for n which doesn't give a prime. Now, the way to check it is that you put in your number. So you can put in 1. Then you have to prove if that's a prime or not. So then to prove it's a prime, you do your proof by exhaustion. And you'll find a counterexample. So if we put in 1, then you get 2 to the power of 2, which is just 4, plus 1 is 5. Now that is a prime. If you put in 2, that's 2 to the power of 4. So you get 17 out of this. That's a prime. And then you keep going. And there is a solution somewhere which gives disproof by counterexample. And I'll do that in another episode because it is bloody gorgeous and you can prove it with a spreadsheet. Now that is good maths. Okay? That is everything for here. Let's rub this out. There's not many key points here other than this. And that's just our initial statement. So we'll have a look at Fermat's prime in a following video. And then we've got one nice big one left. That was it. It's not difficult, this one, is it?